Good morning. Welcome to the third and final webinar showcasing the results of the IMAGINE-B5G project. Today we are excited to have here with us the winners of Open Call 3 that will share the results they achieved through their work within the project. We'll start with a quick introduction to IMAGINE-B5G given by David Gomes Barquero, project coordinator, and then we'll move on to the Open Call presentations. David, the floor is yours.
Yeah, thank you, Daniela, and good morning, everybody. Thank you for joining in this final webinar about our third open call, third and final open call. We have had 15 projects actually in each open call, and well, today we will take a look to the final results and outcomes of the last 15 projects. So just a very short summary or introduction to Imagine Beyond 5G. We are a StreamD pilots and trials for verticals project of the phase 1 of SMEs. We are 17 partners, and we had 4.4 million euros for open calls, and those open calls had to were used for vertical experiments, especially in this third open call, for 7 different verticals that you have here. And in Imagine Beyond 5G, the open callers, they had to go and to one of the facilities of the project that we have 4, one in Norway, well, led by Telenor in France, by Eurecom in Portugal, with IT Aveiro and also Altis Labs, and in Spain, where we had 3 locations, a rural site hosted by Nokia, UPV campus here in Valencia, and also the port of Valencia. And well, we are not going to get into details in the platform, but we tried to, in the project, to reach a common unified platform across the different facilities, exposing APIs to third parties and open callers, and well, each open call project has integrated itself with one of the facilities. And here we have the 15 projects of the third open call. We have classified them as per vertical, although also each of them is associated to one of the facilities. So, well, I'm looking forward to hear the final outcomes and results of the projects. So, Daniela, floor is yours again.
Thank you, David. So we'll now move on to the project's presentations. We'll be starting with the Norwegian facility. So first we'll be having Pulse 5G project presented by Tus.
Yeah, hi. I can share my screen. Okay, can you see the presentation?
Yes.
Okay, so hi all, good morning. This is Tuğçe from Simter, and I will be making the presentation for the Pulse 5G. And our project conducted trial at the Norwegian facility with focus on the 5G powered PLC as a service. Sorry. And our company is Simtera, and Simtera is a product-driven technology company that delivers the Fabmatics low-code platform to help manufacturers digitalize their operations through the industrial IoT, AI, and cloud technologies. And you can see the Fabmatics features and modules. And during the project, we utilize Fabmatics Insight and for the demonstration, and Fabmatics AI for the AI execution, and Fabmatics Gateway for the data acquisition. So in the project, we address Industry 4.0 challenges in automation, rigid PLC hardware coupling, sensor integration bottleneck, and limited adaptability. And we introduce PLC as a service concept, soft PLC, which includes soft PLC, AI-based analytics, and 5G enabled edge cloud orchestration. And our objective was validate end-to-end latency, reliability, and real-time AI control in a 5G industrial workflow. We listed in this slide what we use during the project, but I will explain in detail in the next slide with the basic flow. So you can see we have motor with connected to two sensors, and this was for physical data generation, and we have soft PLC that was collecting data from physical devices and generating high volume simulated data, which is for the stress testing. And we have Fabmatics Gateway. This is for the executing HAI and routing data over 5G to the cloud. And we have network switch to combine all these three components for communication and make the traffic via the Fabmatics Gateway only. And you can see all arrows bi-directional. In our system, the process starts with data collection, then the data is sent to the cloud, and AI model execute, then the results are sent back to the soft PLC. With this way, we measured end-to-end latency of this entire flow. So our validation methodology was to validate full end-to-end system from soft sensor and soft PLC to cloud and back to the edge. We used the timestamp for this latency measurement, and by measuring latency and network performance under real industrial condition using different networks. And we also confirm that our AI-enabled PLC as a service concept works securely and reliable and support future sustainable goals. And of course, we also showing potential for user-friendly interfaces for operators. And you can also see our project and 5G Norway facility connection in this flow. So for trial execution, we execute one full scale scale trial in Norway under real industrial condition using 5G, where we validate the complete pipeline and confirm that the AI-powered feedback loop. But due to the budget and time constraint, the other tests were conducted in Turkey using ADSL and cable. These were not directly, of course, comparable, but help us to understand performance difference across legacy and local infrastructure. And these additional insights support our main goal to demonstrating why 5G is more suitable for industrial control applications. And for the KPIs, you can see our KPI definition and target and measured value. We focus on 6 different KPIs, and all targets were defined at the beginning of the project based on our previous experience and just assumptions. And through the trials, we successfully measured and achieved all the goals. And for KPIs, this slide summarizes our KPIs, and we demonstrate PLC as a service feasibility, ensures secure European data processing with 0 incidents, and shows strong potential for sustainability and inclusiveness, which led to new horizon follow-up project. And our experiment result, you can see the Fabmatics interface. We are showing the end-to-end latency, edge to cloud latency, and the decision. AI decision with its value. So this measurement does not reflect pure 5G latency, of course, because it also includes backend processing and other stuff. But our objective was to observe the full end-to-end latency using the 5G and see its benefits for the future works. And for the impact result confirms strong market potential, cost efficiency, scalability, and competitive advantages, and also full alignment with the European digital transformation goals. And for ethical part, all data is machine generated, securely processed using internal models with traceable output. So we can say we are fully aligned with the GDPR and European AI Act. And for the lesson learned and future direction, we can say our project was successful, validated with 5G and proving reliability and consistent latency. And for the future work, we'll focus on integrating Gen AI with the 5G and scaling data flows and enabling sustainable vendor-neutral automation services. Thank you for listening. I try to be fast.
Thank you, Tuz. So now we'll have Project 5G for Rehab, presented by Nena.
Hello, good morning. I will share the screen. Okay. Could you just confirm that you see in the presentation mode? Okay.
Yes.
Yes. Thank you. Once again, good morning. I'm presenting the open call project, which is very much related to our, let's say, daily business. We are the company which is providing the software for the fitness and the healthcare, which includes wearables and sending the data and processing data from the wearables. This project is concretely targeting one very important use case, which is when you have the athletes, or you can have also the patients who are remotely doing some exercising. Then this data should be transmitted and processed by the medical doctor or rehabilitation expert or trainer who is remotely actually observing everything. And the main goal is to use our technology, which is related to calculating biomechanical parameters of a movement, and then providing different type of the use cases. So this slide illustrates one volleyball player who is wearing the sensor on the back, and we are measuring the different type of the jump parameters. What is the main problem in our, let's say, model is actually that all the part which relates to the processing, so how we are processing the data, how we are presenting the data, is already more or less solved. But the main open issue is actually connection. So how we are connecting the data, which is as I said, collected somewhere, how we are connecting this data to the remotely presented trainer or medical doctor. There are billions of use cases which relate to the telerehabilitation, telecoaching, and this is also a huge market. So what we were searching for was actually how we can do this in a very systematic way by assuming that our use cases are really related to a lot of data. So for the boxing use case, you have really kind of tens of the punches in the second, and we are calculating different type of the parameters like velocity, force, power. So there is a huge amount of the data, and the main KPI is that we would like to have the speed and quality of the data done properly. Let's say speed and quality of the data transfer must be very proper. Whatever does it mean? Obviously, any kind of delays is introducing a problem, and any kind of the quality problems is introducing a problem in calculating our parameters. And this is the solution. So this is actually the example from the chart from the recently done experiment in Norway, in Oslo, in Telenor. So what is the solution is that we have the 5G in the between, which is connecting the training plans which are done by the trainer, by the medical expert. So he's defining, let's say, the training or the therapy. And then by using 5G, this data is translated or transferred to the patient who is getting this training plan on the fly, so ad hoc. And then he is doing exercising. In the real time, this data is sent again through the 5G. Okay, there is a kind of the processing, which is, as you can see on the right-hand side, in the telco cloud. So there is a heavy processing, which is calculating these parameters, and calculating everything what the medical doctor would like to see. And everything is happening in real time because this is a kind of dynamic training. So it's not that the training plan is fixed. Based on the results from the movements, it's called change of direction, the medical doctor can in real time actually change the training plan. And this is actually the top of everything because usually in this kind of the trainings, you don't have the static sequence, but you as a medical doctor remotely observing everything has to have the mechanism to dynamically intervene. And we are really very thankful for the project for having this opportunity because this was the original slide. So this was what we're asking for, and you see that actually we get that what or we receive that what we asked for. So our problem with this dynamically remotely controlled trainings is resolved. This is the test results. Okay, in the report we have really a lot of measurements and a lot of statistics, but just to show something what is for us very important, because before 5G we could have 4G or we could have Wi-Fi. In both of these cases, as you can see on the screen, the receptivity is much better in the case of the 5G. Actually, it's only these use cases are only allowed by using the 5G. So it's also very interesting because we are now also in Serbia. There was no 5G so far. Now 5G is coming with one operator, and we will be using this opportunity obviously to see how additional services based on these results can be introduced. Okay, you see some numbers. I will go into the impact by really showing you the big picture. So you can see now 5G is there, 5G is closing the cycle, but it's actually opening new circles. So what we are doing now in this case was this testing diagnostic, a little bit of therapy, but we can do also real-time monitoring on the field, so not in the therapy. We can do gamification, and obviously the domains are not only sport, health, entertainment, education. So it's really going into a wonderful direction. I would like to present, and this is probably the last slide, even the bigger picture. So what is the very important? If we are getting this 5G transfer data in a very fast way, then we can do miracles related to the processing in the real time, because our technology, as I said, is calculating these biomechanical parameters. We are introducing also AI in order to do recommendation, anomaly detection, prediction, and if everything can be done in the real time, then the use cases are really exploding, as you can see. By the way, we have this augmented reality. This is another big issue here. It's not very important for the 5G, but it's very important for really usefulness and acceptance of the use cases. I would like to thank to the Jane, to thank to the hostels, to the Norwegian facility. Thank you very much. Also, the video is excellent. You can see on the left hand side our colleague in Norway. On the right hand side, you can see the athletes which we are using actually this system. And I really would like to thank you, just to let you know that we are for almost 10 years. We are working on these issues, wearables. Now we are doing with the rings also, and we are introducing also LLMs, feedbots. So this is the beginning of a really very interesting exploitation of the results. Thank you very much.
Thank you, Nenad, for the enthusiastic presentation.
Thank you.
We'll now move to the scanner project presented by Tapani.
Okay, hello everyone. And my name is Tapani Rantakokko, CTO at Finway. And I will present project Scanner. This work has been carried out together with my colleagues Juha Kela, Tapani Jämsä, and Mikko Polojärvi. Our focus has been to improve quality assurance in industrial environments by combining high-precision 3D scanning, XR visualization, and advanced network technologies. In many industrial sectors, field inspections aim to determine if components show wear or damage, and whether they can be reused or they maybe need to be repaired or replaced. And today, these inspections often rely on human sensors, mainly visual and tactile evaluation. Even your fingernails can be quite useful for this purpose. However, this causes a few issues. For example...
Viene se prezentacji, kaži.
Okay, so these
Inspections
often rely on human senses, mainly visual and tactile evaluation, and even your fingernails can be useful.
I think you muted yourself, Tapani. I cannot hear anything anymore.
Yeah, he's muted.
How about now?
Yes, now I can hear you at least.
Okay.
Much better.
Okay, good. I didn't do anything, but I did hear someone else talking, so something happened. Let's go back. So using human senses for these inspections causes a few issues. One of them is that results vary between inspectors, and there is also little measurable evidence to prove to customers the need for these expensive repairs or replacements. So there is a clear need for a more objective, traceable, and collaborative inspection workflow. And in Scanner project, we address this by introducing an automated 3D scanning station, which is capable of creating detailed digital twins down to micrometer level precision. The resulting point clouds can preserve even subtle defects such as scratches and dents. We then use XR to allow experts to inspect, make measurements, and annotate these models. And finally, fast 5G connection enables remote collaboration. Multiple experts can inspect these models together as if they were standing next to each other. The key technical challenge was to render tens of millions of points smoothly on low-cost and low-memory XR headsets. To achieve this, we have developed high-bandwidth streaming from a 5G edge server, combined that with a tiled representation, level of detail management, and memory caching. This system also supports natural cooperation features such as multi-user sessions, voice communication, avatar representation, hand tracking, 3D pen, and even tactile feedback through special gloves. All of this is synchronized with low latency to maintain near real-time experience. We ran 2 trials at Telenor's indoor 5G facility in Fornebu, Oslo. We tested point cloud loading performance and low latency multi-user synchronization. For this performance analysis, we used Kaitotech's COSIUM tool to measure, for example, throughput, latency, and jitter. Our test users performed collaborative wear and tear inspection tasks, and user experience was assessed qualitatively through web questionnaires. The trials confirmed that our visualization pipeline is now scalable. We improved it from 500,000 points up to tens of millions of points without any clear upper limit anymore. Also, advanced 5G network delivered the required performance. Our typical sessions transferred several gigabytes worth of point cloud data without hiccups in just a couple of minutes. And also the latency stayed reasonable under 25 milliseconds. And maybe most importantly, the participants quickly learned to collaborate in XR, and they found it useful for assessing wear and tear. One major insight was the necessity of 5G networks. 5G provided smooth interaction, while Wi-Fi runs showed interruptions and slower tile loading. Overall, for us, Scanner demonstrated that component wear inspection can indeed be supported with digital twin-based evaluation, which offers precise measurement capabilities and remote collaboration. And now our next steps involve preparing industrial pilots and moving towards commercialization. We have several customers who could benefit from this solution already. And if you would like to learn more or collaborate with us, please reach out. We are a research-oriented company from Finland, founded by former VTT research scientists, and we frequently participate in EU and ESA research projects. You can contact Juha Kela, our CEO, or myself. And finally, I want to give special thanks to our patrons Kostas and Fahim for their support, also to Telenor for providing excellent test facilities, and to our local company collaborator Kaitotech for their costume tool and assistance. And of course, thank you everyone for your time and attention.
Thank you, Tapani. We'll now move to the last project from the Norwegian facility, which is 5G Paste, presented by Sebastian.
All right, thank you very much. I'm going to share the screen in a second. Can you see the screen?
Yes.
All right, let me. Okay. Hello and good morning, everyone. I'm here to present the results of the 5G PACE project, part of the IMAGINE-B5G. And let me tell you what it's all about, if my pointer is working. Yeah. So what we want to do is we want to enhance remote multimedia production. So you have a scenario where you want to record something in a remote area, or where you don't have the infrastructure, or very few infrastructure. And usually stuff like editors have to be on site to do low latency editing of the incoming video. In remote multimedia production, we stream the multimedia as directly and raw as possible over a network so that the editor can work in a remote location like at home. The problem here is that multimedia is inherently bursty. So when a new frame goes out, we have a lot of packets which have to be transmitted at once. And this can overwhelm the infrastructure, the network infrastructure, quite easily. And it causes packet loss and it causes jitter, which is to the detriment of the workflow of the remote editor. So our proposed solution for this is pacing. Pacing has benefits to the network in general, but what it does is it spaces out the network packets over time so that you have a more even and smooth flow of packets, which is much more like multimedia, like network equipment is working, and can therefore alleviate the issues of loss and jitter. And to test our theory, we have, or to test this hypothesis, we have set up a test bed with the help of our patron Carsten in Norway and Telenor, which consists of, hang on, let me, nope, that's not the right one. Yeah, which consists of a multimedia source, which we are pacing with the smart NIC. So we have a pacing algorithm implemented on hardware, which provides extremely precise pacing or timing, because it's like the last line before the data goes into the wire. We stream that over the setup 5G infrastructure to our measurement service, which simply renders the video, acts as a stand-in for the multimedia editor, and collects data such as multimedia quality, packet loss, and stuff like that. In between in the network, we have deployed a P4S, or short PASTA node. PASTA is basically a switch which timestamps packets and keeps track of when packets are coming in, and provides nanosecond accurate timestamps for incoming or for flowing packets in the network. So we can really precisely measure where the delay and jitter actually comes from. So we can say, okay, this is from this part of the jitter is from the 5G infrastructure. This part of jitter is from some processing delay on the producer side. So a really handy tool to have here. And what I'm going to show you here right now is one of our first insights. This is a traffic trace of the multimedia of the video that we are showing, the first 3 seconds, and it shows the interpacket time. So on the x-axis, you have the playtime, the real playtime, and on the y-axis you have the time to the next packet. And I want to start to explain it at the very end, at the 3 second, around 2.5 second mark, where you can see it is fairly even. You have a little bit of jitter, but it's usually something around like 30 milliseconds or 35 milliseconds, and this is due to the frame rate of the video, which was at like 30 frames per second. So you get every 30 milliseconds you have in your frame. What is more interesting actually is the zigzags that you're seeing, and this is what happens when a new rendered frame, a new produced frame, does not fit into a single network packet anymore, and then you have a burst of packets which has to be sent out very, very quickly. And you see this happens quite frequently, especially at the start of the video where you have to transmit a lot of information for the first frame. So how does it help us? Well, it informs our pacing strategy and something that we deem as an optimal pacing strategy. So based on this insight, we thought, okay, the optimal strategy to pace our packets for the video frame is that you have some space between the frames. You only have every X milliseconds you have a new frame. And you have a lot of packets that you have to send out until the next frame. So we spread out the packets evenly over the time to the next frame. So right now you can see up on the top here how it is done now. Like the state as is, you have a new frame, you send out the packet as quickly as possible, possibly overwhelming the network. And what we've implemented is now that we are pacing out the packets so that we are finished sending out the last packet for the frame X, and by the time, exactly the time when frame X+1 arrives, which we know because we know the frame rate and we can control the frame rate of the video. So we implemented the strategy, and here are our KPIs. We've achieved very low latency. Actually, this was close to the 0 RTT, so RTT without load on the network. We have experienced very low jitter, where you can see the benefits of 5G, as the other presenters have pointed out. 5G provides excellent jitter. We've achieved decent throughput. We have encountered no video freezes, so we had, with any video configuration that we encountered or that we tested, we had no video freezing and always smooth video. However, one metric that we've always kind of crashed is packet loss. And let's dive into that, because 11.28% packet loss is pretty bad. So where's the culprit? It could be the 5G network, it could be our infrastructure, it could be the measurement infrastructure. And after a thorough investigation, we figured out that the smart NIC, which actually does itself the pacing, is the cause of the packet loss. I will not bore you with details about memory management, but actually we have very limited space to buffer packets on the NIC, so that when we are trying to pace packets, we have to keep them for a while, at least until the next frame arrives. We have to keep them in the buffer. And the very limited hardware space on the smart NIC actually is causing the packet loss. So we have experienced no packet loss in the 5G infrastructure, which worked perfectly, but our smart NIC itself was the culprit in this case. So what have we learned? I think we have shown that pacing offers benefits for the whole network traffic. We have experienced very low latency, no latency spikes, and no jitter, or very, very low jitter. But of course, we need to go back to the drawing board and have to implement the way we do passing much more efficiently, so that we can even sustain loads like multimedia. The hardware-assisted pacing, on the one hand, it it delivered excellent accurate timing. But once you've hit the limits of hardware, you are pretty much done. And so now our approach, and this is hopefully maybe a longer term collaboration with the University of Oslo. We are working on maybe software hardware co-design, where we're doing some parts in software, some parts in hardware to gain the best of both worlds. And we have to do a much more efficient implementation of the whole pacing strategy on hardware itself. So that's it from me, and thank you for your time and for your attention.
Thank you, Sebastian, for your presentation. We'll be now moving to the Spanish facility. The first project will be presenting its ABS 5G with Playo.
Hi, hello everyone. Wait a second. Okay, hello everyone. My name is Playo. I represent UTEC, and I'll be presenting the results of the ABIS project, the Spanish infrastructure. The name of the project is Autonomous Boats for Safety and Security with 5G. This project counted with the participation of Telefónica, Nokia, the Fundación Valencia Port, and the Polytechnic University of Valencia. Here is a small introduction to the system. This use case 4 focuses on demonstrating the potential of the 5G connected to autonomous surface vessels developed by UTEC and carrying Nokia and UPV routers and using the Telefónica 5G network. Here's a little picture of the ground control station that we use and a quick video of the USB operating, which we are going to see much because there's not much time. But yeah, through this demonstration, we aim to show how 5G can significantly improve efficiency and flexibility of autonomous maritime missions. The objectives of the projects were the following. We wanted to achieve and enhance constant 5G connectivity at sea. We wanted to configure the network slicing to improve the signal quality received in the sea and near the coast, and get enough signal quality to allow fluid USB autonomous operations, connected the USB to the antennas in the coast and completing a series of scenarios that demonstrates its capabilities. What are scenarios? Well, these followings. They are focused on public protection and disaster relief, such as search and rescue support, security of certain restricted or protected zone, environmental monitoring, and real-time surveillance and situational awareness of an area in distress. How does the system works? Well, here's a little diagram of the architecture of the system. The diagram shows the network architecture used to control the USB, called Kaluga, via the 5G network. On board of the USB, there is a 5G router that connects directly to the router on the ground control stations through a VPN channel. The ground control station is connected to an internal 5G router via an intermediate router labeled router ground control station, which control the VPN. We use a prioritized slice for emergency services. This slice dynamically reserves up to 20% of the network resources in situations of congestions or heavy traffic, ensuring continuous service and reliability, even under high demand conditions. During the first trial in demonstration, we had a little malfunction on the 5G router in the ground control station, and we quickly replaced it with Starlink, which worked perfectly, which demonstrated that a USB can be controlled via 5G routers from a long distance, for example, from Madrid, without any problem. At the start, we made 2 tests on the Nokia facilities to ensure the ground control station and the Kaluga could connect and share information via 5G. The first test was in April and was the initial contact to make the system work. We faced some challenges due to the absence of a static IP address, but however, we were able to connect both routers to the 5G network and only detect Kaluga's router from the control station. And the second test on June, we managed to create a full network test. The test confirmed a stable communication between the control station and the USB, including video from 2 cameras, GPS, and steering commands and radar data. The KPIs measured here were mainly the uplink and downlink data rate and the RS-RP signal. These trials were very, very viable as they helped align the team workflows and clarify the technical requirements for successful communication in the later demonstrations. The demonstrations took place in Valencia in July. There we tested the system that I described before and performed the use cases that were planned. The USB performed the search and rescue operations to a simulated stranded persons in the sea and executed a surveillance over a big area close to the beach. At the same time, we continuously monitored the signal quality to test the range of the 5G connectivity and how it changed when it changed antenna from one antenna to another along the beach, along the coast. We had very satisfactory results, I must say. This is the area when we performed the majority of the demonstration near the Patacona beach. Here, the USB conducted a surveillance operation and a simulated search and rescue operations. The control station was on the orange point, so we could see the whole operation. The second day, we had to test on the private network in that little spot there on a private harbor, just to test the signal and the quality on the private network. Finally, the main KPIs tested on these trials were the uplink and downlink radar rate and the RSRP, the reference signal received hour. And the results of the operation can be translated into a set of KPIs. Some of them are the trustworthy driving, the trustworthy navigation of the USB, the first responders efficiency, the platform cost efficiency, and the risk for the personnel for the surveillance activities. In the end, the trials were considered a success, and they opened the door for further development of this promising and reliable system. Nothing else. Thank you so much.
Thank you for the presentation. We now have project PortSafe B5G presented by Tkenis.
Hello everyone, give me a second to share my screen. I hope you can now see my screen.
Yes.
Can you hear me? Perfect. Great. So I'm presenting PortSafe Beyond 5G, and this initiative focuses on proactive observation and real-time traffic and surveillance analysis for facility enhanced security under the Imagine Beyond 5G network. So in here, our primary goal was to validate an advanced 5G open platform at the port of Valencia in order to target the intersection of facility security and logistics efficiency. So what's the purpose? Beyond the ports, because the ports are complex environments and face dual challenges. The first one is that they require strict security for restricted zones, and secondly, they need efficient traffic management. And these are traditionally treated as separate problems, using separate systems as well. And this leads to high costs due to manual patrols, some delayed detection of security breaches, and in general, inefficient traffic flow at the port. And this is solved by PortSafe Beyond 5G by creating a single and dual-use platform where we fuse video data from 3 different sources: CCTV cameras, unmanned ground vehicles, and unmanned aerial vehicles, the UAVs. And we utilized the 5G standalone technology that allowed us to transmit high bandwidth video with low latency to the multi-access edge computing located at the UPV. And by processing AI at the edge, we delivered immediate security alerts and valuable logistics data simultaneously. Moving on to the dual use scenarios, which is the core innovation of the project, that is versatility. The platform utilizes the same hardware to operate in two distinct modes. First, on the top, you see the security and safety mode, where the system uses geofencing to monitor restricted zones in real time, and the AI instantly identifies unauthorized people or vehicles crossing boundaries and generate automated alerts in a dashboard. And this way also we ensured worker safety by automatically detecting if the personnel are wearing the required PPE, such as the hard hats. See the red rectangle here. And secondly is the logistics optimization mode, where in this scenario we retask the same UAV and CCTV cameras to monitor parking and container areas. And here the AI analyzes the video feeds to estimate the parking occupancy. And overall, this data helps port operators to improve the traffic flow and reduce the idle time, the dwelling time of the trucks, cutting this way the emissions. Okay, proceeding to the dashboard. All of this data I mentioned need to be accessible, of course, and for this reason we utilized the We.Move platform of Wings as a single pane of glass for all the operations for the operators. And as you can see from the dashboard, we integrated the feeds from the drones, the robots, and the CCTV into one holistic view. We visualized the geofenced zones. We displayed the real-time AI detections overlaid on the video, and we had a logging system for every security and maybe safety event, such as the no hard hat alert I said previously, in order to manage complex logistics and security scenarios from one screen. And moving on to the validation and the results, we validated the system at the port of Valencia. The results met or exceed the targets. On the left, we have the technical KPIs, where we achieved an end-to-end latency of around 42 milliseconds, under the 50 milliseconds targets, which is crucial for real-time control of the robots and the drones. Regarding the accuracy, we achieved around 19%, well above the 95% target, ensuring model reliability for the security. And we maintained 100% reliability on the 5G standalone network during the trials. And moving on to the societal and economic side, the KPIs here. Regarding the security and trustworthiness, we successfully detected simulated threats with over 19% accuracy. We also projected around 30% reduction in CO2 emissions by replacing fossil fuel vehicle patrols with electric drones and robots I demonstrated before. And we also projected an around 12% increase in economic growth, driven by the reduced vehicle processing times I mentioned in the beginning, and better logistics flows. That from our side. Thank you. If these are our emails, if you need to reach out. Hope I was on time.
Yeah, thank you.
Thank you
We'll
very much.
now move on to the project OPS5G, presented by Pedro.
Good morning. I'm sharing my screen. You probably already see it. So,
yes.
Good morning. My name is Pedro Branco. I'm the CEO of Shield Sistemas de Información in Spain. And I was basically coordinating from our side the OPS5G project, which the acronym means Cyber Physical Environment for Real-Time Efficient Sustainable 5G Enabled Farming Operations. So, the project objectives were basically to deliver an augmented reality enabled and AI digital twin, and also to maximize the benefit of existing agricultural technology and operational assets, for instance, satellite imagery, field sensors, while taking advantages of 5G technological differentiators. The trials, tests, and demonstration took place at the IMAGINE-B5G Matanza experimental site in Spain. During the project activities, we achieved TRL6, so the system prototype was demonstrated in a relevant environment. In Matanza, Soria, it's an environment of vineyards, and basically it's a real-life representative scenario where there are different parcels of vineyards with on-site environmental sensors deployed, including humidity, environmental stations, temperature, etc. The OPS5G development and experiment were supported by Nokia, who is managing the Matanza de Soria sites. In terms of experimentation scenarios, and now going, let's say, in the direction of the user side, we basically tested and demonstrated 3 different types of scenarios. The first one was artificially enabled crop health monitoring and resource optimization. The second one was renewable energy artificial intelligence enabled forecast and operational alignment. And the third one was artificial intelligence enabled video analytics for early disease detection. Just a comment, the whole validation campaign and demonstration campaign took place, like I said, in Matanza de Soria. For your awareness, it's a rural area, and the site facility is powered by renewable energy, and hence the relevance of the second scenario. In terms of architecture overview, let's say it's a standard architecture. So from the left, you see the different sensors and inputs. Then via the network, they go to the server where they are processed. The digital twin is generated. The artificial intelligence forecasts and recommendations are also generated. And then again, via the 5G network, they are delivered to the client environment, which can be a smartphone, a desktop environment, and like I mentioned, the augmented reality glasses. So in terms of the augmented reality glasses, we used a custom off-the-shelf product, which is the Vuzix Blade 2, which we have previous experience. Basically, the user has a head-up display in front of his right eye, where he can access recommendations, satellite imagery, data from the sensors, and positioning too. This is let's say, the desktop interface, where you can, again, access the different sensors. So this can be accessed by a desktop, a laptop, or by a smartphone. You can access to satellite imagery, again, like in the augmented reality, and also to the sensor data. Here you have some images of the experimental campaign at Matanza de Soria. Basically, we did 2 rounds of field experiments. over there. Let's say the KPIs that we were aiming to achieve in terms of latency, reliability, throughput, scalability were achieved. You can also, I think, imagine that the end goal in terms of value in the impact is to optimize water and fertilizer usage, operator field time via the use of augmented reality glasses, enable clean energy utilization, and also scalability in terms of deployment in rural areas. And that was my presentation. Thank you.
Thank you, Pedro. We'll now have the presentation of the Holomed project by Mario.
Okay. Good morning, everyone. Let me share the screen and enable presentation mode. Can you confirm if you can watch it?
Yes.
Okay, perfect. So this is Mario Montagut from I2CAD Foundation, and we are going to present the work done and results obtained in the Holomed project, which was about conducting multi-user holoportation trials for an immersive education use case over the UPV testbed, okay, in Spain. So this is the outline of the presentation. We will briefly revisit the objective that we envisioned, the technology that we have deployed and adopted to run these vertical experiments, the trials conducted along the obtained results, and summary of the outcomes achieved in the project, and lessons learned. So the project had 4 main objectives. There is a summary. The first one was to provide a novel network as a code or network as a service API to request quality on demand for a specific traffic flow, in this case, an XR traffic, carrying volumetric video. Objective 2 was to adopt and adapt a real-time multi-user holoportation platform that we developed in I2CAD in previous project. So in this project, we are validating its readiness and its potential impact to run immersive lectures over a beyond 5G testbed. Run a series of both technological and user experience trials in the scope of immersive education, and of course maximize the overall impact for all the involved parties. Okay, so this is an overview of the technology that we developed, but let's not focus on the architecture and focus on what the multi-user holoportation platform is able to deliver. So as you can see in the figure at the top right, you can see that we can have multiple users who can be in different locations, meeting around a virtual table, in a virtual meeting room. So this would be in VR mode. And the figure at the bottom right, you can see my 2 colleagues, Stefan and Mohammad. Mohammad is the guy with a black white shirt, and Mohammad is not actually there, okay? So it's a meeting between 2 users in our I2CAD lobby, but as seen by a 3rd user wearing a headset, okay? So you can have meetings, face-to-face meetings, as if the user were co-present, but one of them is remote, okay? So we wanted to test the readiness of this technology when deployed over beyond 5G testbeds. Okay, so this is an overview of the trials we conducted at UPV. On the right, on the left, you can see me now acting as a professor and instructor, wearing a headset and being captured by an RGBD camera. In this case, the camera captured my full body frontal viewpoint, but we could use multiple cameras to capture my body in 360 degrees. And then we can see 2 colleagues from UPV enjoying their experience as students, okay? So in the pictures, it can be seen a bit abstract, but let me show you short. We have like 5 minutes videos, but I will show you briefly, okay? So what you're seeing in this video, this is me, but projected onto the real immersive lab at UPV, okay? So the lab is real, and I'm projected into the real environment. And now you will see, I will go to second 40, that the video recorded from the viewpoint of the students, okay? So you can see the hand of my colleague Alvaro. So I have deactivated the audio to not cause too much noise, and Juanan also. So they are watching me, but I'm not there. And at some point, I will activate a presentation, okay? So there is no physical screen, but I could present the slides, videos, even if we go to more advanced presentation, I could call colleagues, remote colleagues, and present them as volumetric holograms, okay? So this is a new way of conducting immersive lectures using extended reality technology when the input sources are remote and are connected via beyond 5G networks, okay? And same manner, this is XR pass-through mode because you don't lose track of your real environment. On the left, we did the same with the digital twin of the UPV lab, okay? So this is like, you can do the lessons like in a metaverse environment with remote users, okay? So this is just an idea of what we did. This is another video which shows the Grafana dashboard and the colleagues from UPV experiencing this, but a summary of the results, okay? So when we refer to the XR session, some KPIs are that the bandwidth for the hologram is around 10 megabits per second as expected, and the UPV network, beyond 5G network, was able to handle this traffic without problems. The end-to-end delays when using a communication server deployed at the private UPV edge was around 100 milliseconds end-to-end, okay? And in this case, the reduction when compared to a server in the cloud was around 10% delay reduction. And the network was able to keep the original frame rate for the clients. We conducted almost 20 sessions in 2 iterations. We performed 3 visits to the UPV testbed, around 10 minutes per session. The lectures were not too much long, no, because you're wearing the headset and we didn't want to tire the students. But we performed continuous sessions with sessions over 2 hours, okay? So this is somehow also reflects that it's a large-scale trial. And we also conducted some isolated tests to demonstrate the benefits of the quality-on-demand API, no? And this is shown in the graph that when we apply the quality-on-demand, so we congested the network, and when we apply the quality-on-demand, we could prioritize the XR flow over other background traffic, no? So we are giving priority to the service that you want. Also, in the sessions we conducted, we administered questionnaires to the users, assessing some user experience aspects, like, for example, if the application or the platform performed in a robust and stable manner, the results were super satisfactory. The users were also happy with the visual quality of the hologram, no? Although it has margin for improvement, but they were already able to interact in a natural manner with the professor. The delays were also successful, and in objective metrics, they were around 100 milliseconds. And we also asked the users about KPIs, no? And the opinion of the users was that this kind of technology can contribute to inclusiveness, fairness, and equal opportunities. It can also contribute to environmental sustainability, no? Because you can avoid travels, no? Or also to societal sustainability, no? Because if you avoid travels, you also reduce costs, or it can open new training opportunities or new opportunities to access to services of interest. In this case, it's education, but it could be healthcare, or it could be culture, okay, or even entertainment if we want. And the user strongly agreed that this demonstration has potential to connect and communicate with remote people in a more natural manner than 2D video conferencing, okay? So to summarize, we have delivered like a robust end-to-end XR holoportation platform. The TRL, I would say it's 6 or more. We have delivered a SDK that is compliant with any Unity project to integrate our technology, also datasets with educational content. The camera quality-on-demand API is open source, so we have delivered it as is ready to use by third parties. We have tested this with Amarisoft and Open5G, open source network, with Ericsson network in our testbed at Barcelona, and preliminarily with the Nokia network at UPV. We have also contributed to public and scientific dissemination, like contributing to white papers by 6G AI. And in terms of exploitation, we have conducted trials with 2 universities in Spain, involving 6 professors. And we also did like a trial of how an immersive distinguished lecture of the IEEE Broadcast Technical Society could look like by using this technology. So that would be it. Thank you very much, and thank you very much especially to UPV and the mentors for having offered us the opportunity to run this project. Thank you.
Thank you for the presentation, Mario. We'll now move to the project SMATRA 5G, presented by George.
Hello, I hope you can hear me well.
Yes.
Let me share the screen 1 second, please. There you go. I hope you can see.
Yes.
Okay, great. Hello, I'm Jorge Gallego from Odin Solutions in Spain. I'm going to present briefly the results of our project, the SMATRA 5G, that it's the acronym from Smart Transport with Dynamic Virtual Onboard Units powered by 5G. So the short summary of the project is that our objective is to enhance the connected vehicle capabilities through 5G and beyond 5G networks integration. The idea is that we have virtual onboard units that are basically digital twins of the physical onboard units of the vehicles that are deployed near them and follow them through the infrastructure, so we can improve the energy efficiency and the communications performance. At the end, these virtual hubs act as a proxies for efficient data exchange and also some kind of offloading capabilities. The key feature is that this solution manages this migration between 5G cells for seamless service continuity, so the digital twins can follow the vehicles from up one place to another. Here you can see a brief scheme of the solution where we have our OVU that is located on the vehicle with the counterpart in the edge, the virtual OVU, and then we have two other components, the manager that is in charge of obviously managing all the components, and also the aggregator that acts as an entry point to the system. As you may remember from the previous webinar, we worked with the UPV testbed, and there we deployed our solution. We implemented it there using two Kubernetes nodes that represent the two different domains. They were located in each one of the MECs and near to the two 5G cells that we use. And then on the cloud, we had the aggregator and the manager. The manager also was in charge of communicating with the 5G network, so we can through the monitoring platform and through the NAC and the CAPIF monitor what is happening in the network, because at the end these migrations were triggered when we detected through the network monitoring that the vehicle, in this case this robot, changed from one cell to another one. And then we also have an external consumer that was monitoring all the information that was fed by the vehicle to the system. We seamlessly, to be honest, seamlessly integration with the UPV testbed. They facilitated us a lot the work. This is just a screenshot of their Grafana monitoring, where we integrated all the experiments and we had all the info at one site. We performed 4 different trials. The first one was online with the initial prototype and the basic deployment. Then we did 2 on-site, on-premises trials with the real migration and handover testing, and a second one with a refined migration because we found some places to improve, so we did that, and a final one with a distributed UPF 5G component test, also to see if we had an improvement in the metrics. The setup and execution of these experiments were easy. As you can see, in the initial state is this labeled as number 1. Then we have this robot from the UPV that we used as a vehicle that was established the connection, set up the OVU, and then as number 2 we have the deployment of the virtual OVU, the digital twin of this OVU, and the external consumers start asking for the data from the vehicle that is communicated through all this system. Then we had this situation in which in number 3 the robot moves from one domain to another. It connects to another 5G cell. that is detected through step number 4 by interacting with CAPIF with the UPV's NAC. So the manager detects that this OBU has moved from one place to another and triggers in step number 5 the migration of the virtual OBU, so it can be in the nearest place possible to the vehicle to maintain low latency communications. And finally, in step 6, we can see that the external consumer keeps receiving all the information and maintains the latency. We run the experiments there in the UPV with this robot that, as I mentioned, acts as a vehicle. Here you can see some graphics from Grafana in the top right with the RSRP values from the work we did to simulate all these migrations. Then below we can see the latency measured from this external consumer during one of these experiments. As you can see, even though we have a handover and we change from one domain to another, the latency was stable between more or less 6 and 8 milliseconds to access the data from the vehicle. We also managed to address all the KPIs and KVIs that we stated at the beginning with almost 100% reliability, 99% availability. We were able to position the vehicle in less than 1 second and with a very low service deployment time. Also, all the KVIs we managed to address both in qualitative and quantitative ways regarding the innovation of the platform and the environmental sustainability regarding the energy efficiency. And well, to finalize the key results, we managed to evolve the solution from TRL 3 to TRL 5, and we were able to leverage the IMAGINE-B5G platform. It enabled us to make a quick deployment of this kind of next generation services. All the tools were accessible and easy to use. There was a service interaction with the B5G network thanks to the NAC and to OpenCAPIF, so it was easy to interact with the network from the application. And also we had this real-time monitoring that enabled us to do the experiments. And regarding the communication and dissemination, we already performed a webinar with the University of Murcia researchers. We want to exploit this collaboration and maybe do some trials there too. And also we are working on a conference paper. And well, that will be all. Hope I was in time. Thanks to all, and big thanks also to the UPV's team, to David, Raul, Ivan, and Roberto that helped us a lot.
Thank you for the presentation, George. So this concludes the presentations from the Spanish facility, and we'll now be moving on to the French facility. The first project we'll be presenting is 5G Fire, for which we have Gillian.
Good morning, everyone. Can you hear me?
Yes.
Okay, fine. I'll share my screen. Can you see my screen?
Yes.
Okay. So, hello everyone, my name is Gillian and I present our project, which is 5G Fire, which stands for 5G Firefighters Instant Remote Eye. So at Azuria, our mission is to support responders by enabling early detection using AI, and now with this project 5G connectivity. So today, wildfire detection still relies on fixed camera networks, human patrols, and drones that can only send limited data over Wi-Fi or 4G. These methods work to some extent, but they show critical limitation in real operations, such as no reliable way to transmit real-time HD video for fast decision-making. Also latency and connectivity gaps that makes remote PTZ control impossible. And also onboard processing constraints that prevent fast validation of alerts, especially when the drone is moving. And with 5G Fire, our goal was to remove those constraints. We integrated 5G directly into CAMIA, or AI-powered detection case. This means that when smoke appears, operators receive the alert immediately, can zoom or rotate the camera remotely, and validate the event before deploying ground teams. After several test phases, we conducted our final demonstration at Eurocom in Sophia Antipolis on one of Europe's most advanced 5G open testbeds. The system has to successfully detect smoke in real time, transmit alerts in HD video through the 5G standalone network, and it has to enable remote camera control from the user interface. We shall also validate two processing pipelines in parallel, which are onboard AI inference executed directly on the drone and edge AI inference running on a virtual machine integrated into Eurocom's 5G network. So this hybrid approach should reduce onboard resource requirements and also support our long-term sustainability strategy by offloading parts of the processing to the edge when appropriate. So here you can see images from the final demonstration. Camia is airborne, scanning the area in patrol mode, rotating step by step to cover its surroundings. As soon as artificial smoke appears, an alert is triggered and instantly received on the operator dashboard. The high-definition video stream allows the operator to confirm the situation and, if needed, to respond. So this trial validated the stability of the 5G connection, image quality, and also the reliability of the complete detection pipeline in a dynamic scenario, which is much closer to real-world PPDR operations. The technical results were very strong, so we have achieved 21 millisecond latency, which is below our 50 milliseconds target. Over 37 megabits per second uplink throughput, enabling HD streaming without compression, and approximately 100% reliability, ensuring all alerts were delivered. With this system, fire crews gain a much faster response time thanks to real-time alerts. It also reduces operational costs by avoiding unnecessary deployment, also through remote doubt removal. And finally, it has a very low environmental footprint. So it's about 26 kilos over 5 years, thanks to efficient edge processing. So to conclude, I would like to thanks first Eurocom for providing their 5G infrastructure and technical support, as well as Aerovision and all drones for their collaboration during the flights. So thank you very much for your attention.
Thank you for the presentation. We'll now move to the second presentation from the French facility for the project Airway, presented by Ignacio.
Good morning, everyone. Can you hear me?
Yes.
Thank you. I will share my screen with you. Can you see it?
Not yet.
Just a second, please. I don't know what is the problem.
Do you want me to try and share it?
Let's take me just a second, please.
Yeah, we are seeing it now. Yeah.
Okay, thank you. Sorry. Well,
can you just show it on presenter mode? Yeah, exactly. Right there. Yeah.
Yes.
Yeah. That's great.
Okay.
Thank you.
So sorry for the inconvenience. Okay, this is the Airway project. Our experimentation was in relation to the use case 1, firefighting and forest surveillance. and it was carried out in Eurocom in France. We thought that as aerial resources have the greatest capacity for extinguishing fires, and their use is depending on weather conditions, we could support those responsible for firefighting by proposing a system for identifying which aircraft could be used on each flank of the fire. Let me make a couple of comments about the operational context of firefighting. On the one hand, the flanks of fires can be 10 kilometers apart, so the weather conditions on one flank often differ from those on another. On the other hand, aerial means are varied, and each of them can operate up to different wind speed thresholds. Regarding wind speed, it changes with altitude. Actually, the 100 meters wind speed can be 3 times higher than at ground level. Currently, only metrics are available, and they are provided by portable weather stations. Something similar occurs with visibility. Nowadays, a reconnaissance flight is carried out to decide if aerial resources can be used. With fires covering electric areas and changing more rapidly, our vision is that this can be improved by using a drone to know the exact weather conditions on each flank of the fire. In short, this is the threefold operational problem. Firstly, both wind speed and visibility at height can be measured with a drone on each flank of the fire. We had a camera-equipped drone that had been also validated for measuring wind speed in a wind tunnel as a result of a previous project. The second issue was to guarantee the simultaneous transmission of files, especially a large one with 4K images. It was precisely Eurocom's experimental capabilities that motivated our participation in this open call. And finally, once we had received the meteorological data, we had to transform them into an enriched situational awareness environment for decision making by means of the decision support system hosted in the Eurocom's edge. In this case, we adapted the decision support system from another previous project related to aeronautical weather forecasting. I will conclude showing some images of experimentation in Eurocom. In this slide on the left, we see the drone used to capture and send images and data through Eurocom's 5G network. And on the right, various Raspberry Pis and 5G modems used to validate the simultaneous sending of up to 4 large video files in 4K quality. Here you can see the drone sending data via Eurocom's 5G network with the antennas at the top right of the building. This is a screenshot of the decision support system. On the flanks of the fire selected by the user, the decision support system displays a color code indicating the flight risk for the chosen aircraft at different heights of each fire flank. And finally, a picture of the facility team, my company staff. Well, that's all from me, and thank you for your attention.
Thank you, Ignacio. So now we'll move to the Portuguese facility, the last facility we'll be presenting. And for the first project, we have ADS-5G, presented by Lionel. We can see the screen, but we can't hear you. Oh,
good
now
morning.
We can hear you. Yes.
Okay, good morning. I'm Lionel from UShip, and I'm going to present the ADS-5G project. Firstly, UShip is addressing the problem of high labor costs and labor shortage, not just in the delivery sector, but also in the service sector. In our vision, autonomous delivery robots can be more efficient than humans, making the world more greener, safer, and give humans more free time. So ADS project aims to enhance localization, accuracy, and ensure continuous position by combining 5G and GNSS position. This experiment involved a U-ship autonomous delivery service delivering orders across Altislav's campus. In any autonomous driver system, delocalization is the fundamental feature. So to improve the localization system, our project intended to deploy a FTK reference station connected to the 5G infrastructure and combine sync 5G, GNSS position, and visual odometry to improve robot pose estimation and localization, and demonstrate an autonomous delivery robot delivering orders on the campus. Related to the experiment facility, we have been involved in the Portuguese facility, Altislavas in Aveiro, and we took part in the vertical transportation and logistics. Well, this is diagram that summarize how the demonstration of the autonomous delivery service worked from the end use perspective. Okay, it starts with the user sign in, next placing a delivery order between two locations, and this activates the robot flow. So the robot goes to point A to collect the order. Next, the robot drives to point B carrying the package, and a notification with a link to track the robot is sent to the final user. The project timeline occurred as planned with a few delays and adjustments. Just saying that the trial occurred in 3 phases. The first run took place in June 20, the second on August, and the final on the September 29 and 30. The general setup for those trials is illustrated in this diagram. Briefly, the robot connects over the 5G private network through CPE and using a GNSS receiver, the system on the robot starts request support to the GNSS server on cold start to accelerate the first fix, receives FTK corrections from the FTK base station, and 5G position data from the run via LMF. The delivery missions are downloaded from the U-ship platform through a REST API. So here is a photo gallery of the trials developments and a few screens of the tools used during the trials. And now let's see a short video showing the system in action. Okay, and the KPIs for this experiment included the latency when receiving 5G position measurements and FTK corrections, the time to obtain first fix on cold start, and obvious the position recurrency. And analyzing the third and fourth columns is possible to conduct that the proposed target values were achieved. And the KVIs, the project was focused on the reduction of the distance travel and the number of errors during a route, and the increase of average response time on performance maintenance, for example, on remote control or assistance. And thank you to all, and thank to our patrons, Carlos Marques and Bruno Mendes. Thank you.
Thank you for the presentation. We'll now move to the project 5G Ever, which will be presented by Tiago.
And hi, good morning. It's a pleasure to be here. Let me just share my screen, and I think you're set up with my presentation.
Yes.
Perfect. So I'm Tiago Dias. I'm Innovation Manager at A2B. I'm going to start talking a little bit about, sharing a little bit about A2B with you. A2B is a mobility technology company. We work in three main areas. Tolling technology, so you see a lot of equipment here on the roads. We have different types of solutions for tolling vehicles. This is one of our core areas. We also have solutions for traffic management and also urban mobility. And we go from the roadside, from equipments to back offices, control rooms, all the software, or many hardware involved also. It's all part of our portfolio. But as you'll see in this project, we want to get rid of many of this hardware. So imagine a world where you could pay for services with your car. You don't need any sticker tags, you don't need license plate recognition. Your car communicates with the infrastructure. That's what we've been implementing. And in this project, we are very happy to be able to participate here in the IMAGINE-B5G project. And we were able to bring this solution to the 5G network. And you'll see why this is very important. Well, we have the car, and the car has an onboard unit. Most vehicles have this from factory now, and they come equipped with this technology. And we have the 5G network. What we trial and we implemented here is a solution that it has, in this case, we used it for tolling passages of roads and using highways, for example, but it can be used for parking, for charging EVs, anything else. And we have a position where we pass the vehicle and a tolling is paid at that position. There's an actual transaction, a commercial transaction going on. This is all done using the 5G network now. And why is this very important? Because the 5G network is already deployed. You have the 5G network on the roads, near the parking lots. All of that is deployed, and the vehicles have it built in. So it's very different from our previous solution, where we had to implement roadside units to communicate with the vehicles. So this is probably the way to go in V2X tolling. Well, our project is called 5G Evers, for 5G Edge V2X ecosystem for revenue collection. We are clearly in transportation and logistics. We did our trials here in Portugal. And we went from a TRL of 2 in terms of the 5G concept and of 5 in terms of the V2X tolling prototype that we had into a 6 TRL with the trials. I'll show you a video with the trials. So
today we're here in Aveiro for the final trial of the 5G Ever pilot. 5G Ever is a pilot applying 5G technology to V2X tolling. 5G technology is already present in modern-day vehicles. So this was a totally natural step for A2B to evolve our V2X technology here, and it was a perfect fit with the IMAGINE-B5G funded project. We are here in Altis Labs, which is the Portuguese test facility for the IMAGINE-B5G project, and we're also working with Capgemini and IT Aveiro. In this 5G Ever project, we achieved transactions under 40 milliseconds, which is very good. We are not just imagining the future here, I think we're building it, and this is a seamless and safer and more sustainable future. We're sure at A2B of this.
I hope you had sound in the video. I think I was sharing with sound. If you want to see, this is just a shorter version of the video that we did for the project. You have more details. If you want to scan this QR code, you can watch the video on YouTube with a few more details. You can also send some questions my way, and we'll get back to you on that. Well, just to finish up, I'd like to present, I think one of the most relevant parts here is really validating the solution and making sure we are ready to take the next steps. This was very, very well achieved in our pilot. Latency, we had a clear target under 250 milliseconds. We were well below that target with 44 milliseconds for the entire transaction. So the vehicle announcing itself, the tolling transaction being sent to the MAC, and the transaction being confirmed to the vehicle. So we had very good results in terms of latency. Also, fantastic results in terms of transaction success. We did a few runs. We could do more prior to going into production, but this was only for the last trial. We had already done quite some transactions in the first trial. As for location is very relevant for this use case. Being able to locate the solution well is critical for this use case. We were able to achieve location accuracy under 2 meters with the GNSS from the OBU we were using. We're not using the OBU of the vehicle. We were using a third-party OBU with 5G, but we were able to achieve under 5 meters of under 50 centimeters of accuracy just with the GNSS. As for the 5G positioning, we did trial it. We were using only, and the facility was using only one method to estimate the 5G position, and it had some issues. We were able, during the project, we were able to increase the resolution and the accuracy obtained, but still it's not accurate enough to work with, as you can see, with a 36 meters accuracy or error in this case. But it's now clear for the facility and even for other partners how it's possible to achieve better results and what we can explore in the future. So it was a very important analysis at this stage regarding the 5G accuracy and the 5G positioning overall. We were very happy to be able to achieve this within this project. We will now be exploring this 5G V2X tolling solution or V2N tolling solution. And basically, as I said, the accuracy of the positioning still has some challenges that needs to be explored in future projects and in future endeavors. And we're available also to explore this with Altis and Capgemini in the future. We are thinking of doing outside of the project some trials. We're still available for that, Carlos and Bruno. And very well, this is all I had for you. It's been a pleasure participating in this project. Thank you.
Thank you, Tiago, for the presentation. We'll now have the project Neuronet presented by Flavio.
Hi, Daniela. Good morning. Can you hear me?
Yes.
Okay, let me share my screen here. Okay, hope you can see it.
Yes, you can see it.
Okay, so good morning. Thank you for the opportunity for being here. So I'm presenting Neuronet. I'm Flavio Silva from the University of Minho, but we also work with Omnium AI, which is a startup that was created here in the Department of Informatics. So we're close working together. And the idea is to bring and apply AI and data science to diverse vertical domains. Well, so what's the context here? We have the modern infrastructure. Our digital infrastructure today is based on data centers and on the networks, and the mobile networks is really an important component in this area. Well, so what we have here is that we have a rising energy consumption and a carbon footprint of the ICT systems. Although we're trying to be more green, in fact, we're using more energy, especially with the new AI infrastructures that are being deployed worldwide. Well, so we have a lack of real-time visibility about the consumption in the data centers, in the RAN, the transport in the core. And we have no intelligent automation deployed proactively to optimize energy usage. So sustainability and AI, they are mandatory pillars for future networks. And so NeuroNet addressed this gap. Well, this is the overall view of NeuroNet. What we have here is a platform that enables sustainable next generation networks. And NeuroNet delivers AI ML-driven energy-aware platform. Full MLOps lifecycle inside this platform. We can support different approaches here. A support for a multi-tier telemetry and a closed-loop orchestrator. We call it this neuroscaler, which is capable of scaling, migrating, and optimizing services. Well, its applicability could be for the core, for the RAN, for the mobile multi-access edge computing, data center service, and also vertical applications. So NeuroNet brings intelligence, automation, sustainability into the same control loop. Well, concerning to machine learning frameworks here on this experiment, we developed different pipelines to test them. So first of all, we grab the data from the infrastructure and we developed an energy prediction pipeline. The idea is to predict active power usage. We also created a latest prediction pipeline. We're using a similar machine learning stack. The idea here is to predict service latency. We also exploited temporal fusion transforming, which is a deep learning which uses multivariate forecasting, so using different types of features or information to the prediction, and also an IT transformer pipeline. The point here is that NeuroNet can support this and several other pipelines that we can deploy, and we can streamline the operation. We used two use cases in the project in this vertical experiment. So the first one we call the sustainable data center, which is the goal was to reduce energy consumption of cloud native services running on top of Kubernetes. So what is the scenario? I have an HTTP microservice deployed on a K8s cluster. We have Optimeter providing this multi-tier in-depth telemetry. And then we did three phases on this experiment. First of all, we did we call a baseline where we grabbed the data from the infrastructure. We used the service and grabbed the data. This was the data, most important data to develop the models that were deployed inside NeuroNet. Then we did an experiment, so a kind of experiment using the K8s or horizontal pod outscaler, HPA, which is the one native scaler that Kubernetes has. And then we used the NeuroNet outscaler, the neuroscaler, and see how it performed. So what are the advantages here? First of all, we used the machine learn for active power prediction. So we use these features: CPU load, memory usage, swap usage. These were the most important features that contributed for the forecast. So that pipeline that I presented previously, it could receive different features and predict. These were the most, let's say, features that contributes to this prediction. So we integrated this in the pod level, bare metal, and PDU energy level. So we have information from different tiers, and we are using all this information together. So we could provide a more accurate scaling while we reduce the replicas and the watt hours consumed. This picture here presents the overall view of the use case. As you can see here, we have two clusters. One is the clusters that supports NeuroNet, and the other one is the test cluster where we are running the services. This cluster was kind of, let's say, a high availability cluster with 3 masters and 3 workers. So let's say a real world cluster that I can run services. NeuroNet runs on top of that. Here you can see neuroscaler, the different components, and the idea of consuming the pipelines and then actuating in the infrastructure. This was all deployed in the infrastructure of the IT Avero facility. Here we have some pictures of the data centers. They were deployed here in the data center at Avero. Well, then we have a second use case we call the green network service migration. What was the goal here? The goal here was to select the best placement of the services. So we have a multi-access edge computing, and we have the core. We have different services deployed, and the idea was to select these different services. So we have the UE connected to the RAM. We have this local breakout infrastructure. So we use an uplink classifier, and then we could select two different paths for the service. Well, so the service could run. We selected a low energy device, kind of an ARM device. We have an x86 server local, and also we have a remote data center node, a bare metal that was remote after the 5G core. Well, so what the neural net enabled here? So first, a dynamic service migration based on the machine learned predictions, energy aware selection of the processing domain, so local or remotely. Locally, we could even select two different devices. And the point is, well, you should say, if you run everything in the ARM, you have less energy, but the ARM may not be capable of running all the users that could be want that service on the moment. So the idea was to balance the workload between locally, and if necessary, you could move to the x86 and then the remote. This was, let's say, how we envisioned this, but we let Neuroscaler to do these decisions. So the idea here is the reduction of also of the backhaul usage, also the energy for the transport and also latency. So this is the overall view of the deployment. There's a lot of things in this picture, but let me just try to present briefly. We have here in the right side the same neural net infrastructure deployed at ITI Avera. We also have the network. So to have a better understanding, all these elements, they are connected to the PU. So we have this real energy consumption. So we have here a local K8s cluster here for the local processing. So we have the service that we have three. We can see here three instances of the service. The instances that are run on the ARM, on the server, local, and remote after the network core. Another server use the same server here to have, let's say, the same type of energy consumption profile to verify, measure this better. So we have the UE, the RAN, they were deployed at Avera, and the transport switches through the core. Here are some pictures of our deployment there. They're also done in the ITI Avera facility, and we have as well the neural net cluster deployed at the data center here. Well, so let's talk about results and impacts. I'm using more of the time. Sorry, guys, for that. So these were the trials that we did, several trials. The first was for initial data collection, and then we did further data collection and analysis. We did a complete data collection. So, and after that, we did the experiments for use case 1 and use case 2. These are some results for use case 1. As you can see here, this is what I'm presenting here is what we call the model predictive control outscaler that is inside Neuroscaler versus the K8s horizontal pod outscaler. This is the total energy consumed. In the second here, you can see let's say here we can see the replicas. So you can see here the blue here shows the Neuroscaler number of replicas. We see a small number of replicas. Here we have the results from EC2. This is when we use the neural net policy for the service replacement, and here when we use a random policy. This picture here shows clearly that kind of, let's say that the system learns and then it lows down the consumption after its execution. Well, so we did this in a real environment, in a telco grade data center, and we could go from TRL 4 to 7. Well, these are concerning the KPIs here, some information. So we selected 3 different KPIs. The first one is important for both use cases. The other 2 more related to the first one. So the active power, the number of the average number of running service instances, and the average CPU load per pod. As you can see here, we are expecting 20%. That was our goal. This was the measure in the use case 1. So a number less than it would be good, 10% less. We got 28.25. For the use case 2, this 20% would be 106. We got 64 for the UC2. Number of replicas, these are more related to the first use case. But we see here a significant active power reduction consumption, fewer replicas, and the machine learns allow the detection of the energy consumption trends while maintained service level objectives in this case. Here are the KPIs.
Sorry, Flavio,
Oops.
could you please wrap up your presentation just
Okay,
because we are short on time?
Okay, sorry. Well, so these are the reductions we have for the use case 1, 25.75 and 51.28 for the use case 2. So we can see here consistent energy reduction, and we have a minimal viable product here. So to conclude, we have a new paradigm here: AI native orchestration, energy visibility across all layers, real-world 5G integration, a modular, open, programmable platform here, ready for evolution to 6G. Well, our neural net can be this enabler for this energy-aware, AI-driven network. Some next steps, publications, we submit to ICC, UC1, UC2 under preparation, federation across multiple facilities, deploy new pipelines, expansion to other verticals, integration with ORAN, which will be very interesting as well. And last but not least, we can exploit neural net to enable sustainable network as a service. Thank you, and sorry for the extra time, Daniela.
Thank you, Flavio. So we'll now move on to the last project from the Portuguese facility and the last project presenting today, which is WINGS, presented by Abdul.
Hello, everyone. Can you see my screen?
Yes.
Right. Hi, everyone. My name is Wahab. I'm going to present on WINGS project, which stands for Wireless 5G Time-Sensitive Networking for Smart Factories. So I'll start off with a quick introduction, why we started on this journey. When we started this journey with our manufacturing partners like Rolls-Royce and Airbus, they first asked the question, a very simple question: is 5G is actually the right technology for future factories? We tested and proved that 5G is the right technology, and once we demonstrated that 5G can handle high density environment, the mobility and reliability required for manufacturing floor. During the testing, what we faced is some of the key features required for manufacturing are missing from 5G, such as TSN. This technology already exists in the wired industrial network to provide precise timing, deterministic behavior, and micro level synchronization. But manufacturers rely on this for real-time control, but wired TSN limits the flexibility. So this challenge became, so we took that challenge and see how we can bring this TSN grade deterministic characteristics into wireless network. So why wireless TSN? This is our own manufacturing.
Sorry, we are only seeing the first slide.
Right.
I don't know if you have already changed it. I think so.
Yes, I have changed it. Can you not see? Okay, let me try again. One minute. Can you see it now?
Yes, now I can see it.
And is it changing?
Yes.
Right.
Thank
okay.
you.
Wireless TSN. So this is our own facility at AMRC in UK. We have two cells. These are not related to the project, but they are quite important to understand the requirement of future manufacturing facilities. On the left-hand side is a robotic assembly cell. It needs tight timing and sub-level, micro-level millisecond latency to control the robot's movement in real time. And on the right-hand side is an AI-based defect inspection system. that pushes high bandwidth video constantly in upstream. Both need reliability, but they need very different network behavior. Traditionally, wired TSN handle this really well, but it is noted everything is bolted to the shop floor. So manufacturer requires mobility, robots that can move, tools that can be repositioned, and inspection stations that are not tied to cable trays. So that's why we started this project. And so this is our architecture with two key features which we have integrated into the 5G system from TSN. First one was time synchronization using IEEE 1588 v2 version, and then time-aware scheduling using IEEE 802.1 QBV. So traffic from these multiple cameras, which are there on the left-hand side, enter the TSN switch, passes through this TSN translator, which we build, and then goes into the 5G UE. And on the network side, we have the network side translator. All of this allows us to test whether 5G can preserve priority, timing, and determinism end-to-end. Yeah. So these are some of our results which we tested during high and low network load. Throughput remained consistent across high, medium, and best effort, whereas latency. Whereas we have a packet loss, we have 3 different VLANs for 3 different cameras. In terms of latency, it was around 7 millisecond, which meets the tight requirement of 10 millisecond, which are required for many real-time use cases. Jitter stays below normal, below 1 millisecond, which is quite critical for precise closed loop control. Yes, we went to for trials as well to ITU Vero site in Portugal. We streamed multiple cameras. You can see on the screen with high priority, medium priority, and best effort, all these through TSN over 5G setup. And you can see in the next picture how it's behaving. So on the left-hand side, you have high priority where you don't have any packet loss. In the medium priority, you can see some of the packet loss happening. And the last one is best effort, whatever is remaining in the 5G network. You can see it here. In terms of KPIs, we managed to achieve less than 7 millisecond. Jitter was around 0.8 millisecond. And then we also managed to do the time synchronization. Packet loss was a bit too much, which was around 30%. But it was mainly due to the scheduling that packet needs to travel into the second one. That's why we were having the packet loss. But we are still investigating this and working on this to improve it. And yes, thank you very much. And I would like to say thank you to the Vero team, especially to Danielle, for supporting the trials during the overall project. Thank you.
Thank you for the presentation. So this brings us to the end of the presentations for all 15 projects of OpenCall 3. On behalf of the IMAGINE-B5G project, I would like to thank all OpenCall 3 speakers for presenting their results today here at the webinar. And of course, thank all of you in the audience for being here with us this morning. If you have any questions, please don't hesitate to reach out to the IMAGINE-B5G team or directly to the OpenCall projects. This session will later be available on the IMAGINE-B5G YouTube channel. So thank you once again and see you next time.
Thank you, Daniela. Thank you
Thank
all.
you.
Bye-bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you. Bye-bye.